here's the agenda for Module 2. In between each presentation, it's a little tight, but if we have some time, we can take a break in between presentations. We'll begin the day with a presentation on stormwater calculations, and that's presented by myself. And then we'll move on to soil testing, presented by Lisa Schaefer, and that's followed by a presentation from Dr. Dick McGee from NJCAT, and that'll be on MTDs. And after those three presentations, we'll end the day with a quiz 2, and then we'll proceed with the quiz review. So let's get started with our first presentation for today, which will cover stormwater runoff calculations. This material is included in the course because the DEP has found from previous conducted audits of the MS4 permittees that stormwater calculations are oftentimes not performed correctly. So while most of you are probably familiar with these methods, as evidenced by some incorrect calculations in the project submitted for the audits, we included this brief review in the course, and later presentations in Module 3 will highlight some of those errors more specifically, as will the example projects in Module 4. So the 6 major goals of this presentation are: 1, to cover the calculation methods allowed under the Stormwater Management Rule. 2, how to use the National Resources Conservation Service, or NRCS methodology, that's formally referred to as TR55, to calculate peak flow rate, volume of runoff, and produce hydrographs. And NRCS was previously known as the Soil Conservation Service, or SCS, so you may still see the NRCS and SCS acronyms used interchangeably. The third goal is to calculate the time of concentration, and we'll cover some of the examples in our Chapter 5 for the of the NJ BMP manual. After that, we'll go over the NJ DEP 2-step method for calculating runoff from an unconnected impervious area. And then we'll cover when exfiltration may or may not be used in stormwater routings. And our last goal is some instruction on the way to use the rational method to size a manufactured treatment device, or MTD, and that's using peak flow rate as a design criteria. So to comply with the rules, when there's a major development, stormwater calculations that are associated with groundwater recharge, stormwater runoff quality, and stormwater runoff quantity are required, and the rules are very specific as to the methods that may be used. So the requirement is found in the rules at the location noted in green here, which is 7:8-5.7A1. And we can take a look at Romanet number 2 on the list first, since it's the lesser used. So the 2 methods listed here each have limitations as to what they can calculate, and so they're often used in conjunction with each other. The rational method is used for determining peak flow rates, and the modified rational method is used for hydrograph computations. The rational method has been around since roughly 1889 and is used to estimate peak flow rates for specific rainfall intensity, but it cannot provide total stormwater runoff volumes nor produce hydrographs, for which we use the modified rational method. There's more info on these methods in Appendix A9 of the New Jersey Soil Erosion and Sediment Control Standards, published in January 2014, which is available at the link at the bottom of the slide. And we'll talk a little more about the rational method towards the end of the presentation. After the draft revision to Chapter 5 of our BMP manual was published, we received a lot of comments requesting we eliminate it. However, it's in the current rules, so it's still allowed for the time being. And for the modified rational method, if you want more information, this information is included in detail in Chapter 5, and you can read it on your own there. So the first method listed in the rules is the USDA Natural Resources Conservation Service methodology, or NRCS methodology, which was additionally described in TR55. However, TR55 has been superseded by the National Engineering Handbook, NEH, in Part 630, Hydrology, and a link to that is also at the bottom of the slide. The NRCS methodology method can provide total stormwater runoff volumes the peak flow rate, and produce hydrographs. Under the NRCS method, different synthetic rainfall distributions and unit hydrographs can be applied to produce the stormwater runoff hydrographs in accordance with geographical differences that may affect the rainfall pattern of each storm event and the runoff pattern in each region. And that's dependent upon factors like land, slope, and ground condition. And there are plenty of software packages that use this methodology, and in later presentations, you'll learn what to check in your reviews. The NRCS method can be used for a drainage area of any size, but the area is subject to the rule requirement that the relative stormwater runoff rates and/or volumes of pervious and impervious surfaces be separately considered to accurately compute the rates and volumes of stormwater runoff from the drainage area. But we'll get into that a little later on. So now let's take a closer look at the NRCS methodology. So the NRCS runoff equation was developed to estimate total storm runoff from total storm rainfall. The soil and cover conditions determine a parameter called the curve number, which you might see abbreviated as CN. And that will be discussed shortly after we look at the equation that uses that parameter. So we can calculate the runoff depth Q in inches by using the NRCS equation. P is our rainfall data for a particular design storm. The next parameter is initial abstraction, I sub A, which is the stormwater volume loss before runoff begins. It includes water retained in surface depressions, water intercepted by vegetation, evaporation, and infiltration. For New Jersey, initial abstraction is equal to 2/10 the potential maximum retention S, for which we need the curve number to calculate. And after determining the curve number and calculating S, we are able to calculate the total depth of runoff. And so that brings us to a discussion on curve numbers. The curve number is an empirical parameter used for predicting direct runoff or infiltration from rainfall excess. CN is a function of the hydrologic soil group, or HSG, and land cover, such as woods, pasture, agricultural use, percent impervious. HSGA is the most permeable group and produces the least amount of runoff when thoroughly saturated. And the designations go alphabetically from B to D, with D being the least permeable group and having the highest runoff potential. The preliminary soil group classification can be found on the NRCS Web Soil Survey, but further investigation may be necessary, and Lisa will cover that in the next soil testing presentation. And she'll also go over the default HSG values you can assume. So once you've determined your HSG, you're using the defaults that are allowed, you can determine the curve number value to input. Shown on the right is table 9.5 from the NEH. There are also many different land uses and ground conditions, but most of the time you'll see the ones listed here in table 9.5. Notice that the CN increases as the soil group goes from A to D. So there's going to be more runoff for a D soil than for an A soil for a given land cover. It's crucial to use the CN value that best identifies the ground cover type and hydrologic condition. If the analysis uses pre-development CNs that are lower in value, the analysis is conservative. But if the analysis uses pre-development CNs that are too high, the analysis is considered incorrect. Note the requirement from the stormwater rules shown in the yellow box at the upper left of the slide regarding which CN value to use. And the arrow here on the right indicates the particular row where this CN value is. That's in table 9.5, and this requirement also appears in local SCOs. Remember that for impervious surface, the curve number is always 98. And lastly, note the cautionary info in the white box on the bottom left of the slide. That means the values in the red box on the table are not what you will typically see in your calculations for a development project. So what do you do when you have more than one curve number on a site? Due to the nonlinearity of the equations and losses from initial abstraction, it's important and also required in the rules to compute separately the runoff volumes from pervious and impervious areas instead of averaging the curve numbers. Particularly for the smaller, more frequent storms, averaging underestimates the volume of runoff generated by the impervious surface on a site that also has pervious land cover. And using a composite CN value is a common error that we found in our audit reviews. So for example, if we analyze a site with 1 acre of impervious cover with a CN of 98 and 2 acres of grass lawn with a CN of 65 for the water quality design storm, using a composite CN for the site would result in roughly 70% less runoff volume than if the volumes were calculated separately for pervious and impervious areas. So using a composite CN means the BMP is likely undersized for the smaller storms, including the water quality design storm. And when that happens, the BMP does not merit the pre-approved rating for total suspended solid removal. So here's a better example from our chapter 5. I'll just read you the prompt here. A portion of a major development consists of a 200-foot wide, 25-foot long impervious surface and a 200-foot wide, 75-foot long grass lawn area that are separated by a grass swale. The soil is identified as HSGA. The 2-year design storm produces 3.5 inches of rain over 24 hours, and the slopes of the impervious surface and grass lawn are both 1%. It's asking us to compute the volume of runoff that is produced. So from the example diagram, we can see that runoff from the impervious surface will flow directly into the grass swale, so it's directly connected. When looking up the CN for grass from table 9.5, which you just saw a couple slides ago, we get a CN value of 39 for HSGA soils. And of course, the CN for impervious cover is always 98. So next, we'll calculate the volumes produced from the storm using a correct method, which is calculating pervious and impervious runoff volumes separately, and we'll also see the incorrect averaging method. So using the NRCS runoff equation, we calculate S, the potential maximum retention, using our CN values, and input the rainfall data to calculate the depth of runoff, which we then multiply by the area on which it falls to compute the volumes. For this example, look to the yellow shaded box. Averaging the CNs yields a volume that is only 37% of the total volume we calculate when following the rule requirement to compute runoff separately, and that's shown in the green box on the left. So calculating the runoff from pervious and impervious surfaces separately yields a total runoff volume of 1373.3 cubic feet, while using the incorrect composite CN value for both surfaces only yields 508 cubic feet. And so this is a simple example, but it does a good job of illustrating how different the results can be and why we always use the method that's identified in the green box. So moving on to goal number 3, time of concentration. Previously, we saw the definition from the rules that it is the time required for stormwater runoff to travel from the most hydraulically distant point on a site to a point of analysis. T sub C is an important parameter to get right in the calcs. So let's take a look at the next graphic to understand why. And a site consists of one or more drainage areas, and a drainage area is a land area where all stormwater runoff produced by that area converges to a single point. Drainage areas are sometimes also called drainage basins, which are determined by the topography. They can range in size from very small up to millions of square miles. By looking at this watershed, you'll see that due to the slopes of the area, any drop of water that falls in the valley between those two yellow shaded areas, the crests, will eventually make its way to the river, and any drop of water that falls on the other side of the ridgeline within those yellow areas will flow somewhere else. Remember that the most hydraulically distant point doesn't necessarily mean the furthest point in distance. In this image, the surrounding terrain on each side up to the ridgelines are part of the drainage area depicting runoff to this POA marked by the red dot. Therefore, even though runoff has to move much further to get from the mountains to the outlet of the river, the most hydraulically distant point may be somewhere in the forest. In Module 1, we learned that various land uses, slopes, and other factors all affect how fast stormwater actually moves across the land. For example, dense vegetation like forest causes runoff to move more slowly than smoother land surfaces, and steeper slopes cause runoff to move faster. To compute the time of concentration, surface roughness, channel shape, and slope are the three parameters that must be characterized for each segment of flow along the flow path. Additionally, the energy level of the flow also factors into the calculation. The three types of energy the flow may exhibit are sheet flow, shallow concentrated flow, and channel flow. The two most likely to occur in calculations are sheet flow and shallow concentrated flow. And most of you know what I mean by those three flows, but just to be thorough, sheet flow is usually at the headwaters and over plane surfaces. This is where runoff forms a thin sheet that is low in energy, also low in velocity and depth. This is what you may see on lawns or in parking lots. In Chapter 5 of our BMP manual, we note that sheet flow does not occur after 100 feet, and there's more to cover on that in a few slides. Shallow concentrated flow occurs where runoff begins to coalesce and pick up velocity. The depth is greater than 1/10 of a foot and doesn't really have a defined channel. And then lastly, we have channel flow that can be seen in aerial photographs and on GIS and USGS maps. It is essentially flow in some type of bounded channel, which is higher in energy state and relatively faster than the other two types of flow. Now that we covered the types of flow energy, we can put them to use. So from the NEH, the velocity method can be used for a project site or drainage area. Remember that the time of concentration is the sum of all the travel times for each type of flow in a segment along the most hydraulically distant flow path. And you can have more than one occurrence of sheet flow, for example, because one of the defining parameters such as slope has changed. This requires a calculation for each type and instance of flow over the segment or path in which it occurs, and then simply adding them up. Just to note going forward, the assumed minimum value of 6 minutes previously published in our BMP Manual Chapter 5 must now be replaced by a correct calculation. Therefore, it's important to check the reported values in your reviews. If the T sub C is calculated incorrectly, it could potentially impact the neighboring land, the infrastructure, or even a local waterway. So Chapter 5 also changes the maximum sheet flow length in accordance with NEH Chapter 15. For the pre-construction condition, assume that sheet flow occurs for up to a maximum of 100 feet, unless there is something physically in contact with the flow of stormwater runoff, such as a swale, curb, or inlet, to prevent sheet flow from occurring. And that could be by even increasing the depth of flow in excess of 1/10 of a foot, regardless of whether the surface is impervious or pervious. If the site conditions only create, say, 75 feet of sheet flow, use 75, but the max value is 100. For the post-construction condition, the maximum distance for which flow can occur as sheet flow L must be calculated using the McEwen-Speece limitation seen here, but is also capped by the 100-foot max. So if the sheet flow length calculated by the McEwen-Speece limitation criteria exceeds 100 feet, the sheet flow length must be limited to 100 feet. But if there is a site condition which limit sheet flow from occurring at a length calculated from the McEwen-Speece limit equation, even if it's under 100 feet, you can use that reduced sheet flow length. So now let's go into discussing what these variables are. So this is the travel time equation for sheet flow. These are the parameters that must be identified. The NRCS methodology uses Manning's kinematic equation for computing the travel time of this segment. The sheet flow length may be a length that does not exceed the maximum sheet flow length calculated using the McEwen-Speece limitation, or 100 feet, whichever is shorter. The roughness coefficient, Manning's N value, is found in Chapter 15 of the NEH. It's a measure of the roughness of a surface or a measure of the surface's resistance to flow. There are different tables for each energy state of flow. The roughness coefficients for sheet flow are organized from smooth to rough. If, for example, a site has dense grasses, use the Manning's N value of 0.24 in the equation for calculating the travel time for sheet flow. Note that the lower N values, or the lower the N values, the quicker the runoff will travel. And for example, impervious surfaces have a roughness coefficient of 0.011. The NJ-BMP manual states that the maximum roughness coefficient for sheet flow in New Jersey is 0.4, and that corresponds to woods with light underbrush. So in a little bit, we'll calculate the travel time for sheet flow in an example. Okay, so moving forward, let's find the 2-year 24-hour rainfall depth. This is a screenshot from the NOAA Precipitation Frequency Data Server. After navigating to the NOAA Precipitation Frequency Data Server, we got here by selecting New Jersey, and then precipitation depth and partial duration for the time series type. You will end up with a chart like this one, but extending a little further in duration and storm recurrence interval, where you can find the column for the 2-year storm rainfall distribution, and then the row for the 24-hour duration. And the rainfall depths are listed in inches here. So from this chart, the rainfall depth is 3.33 inches, and that's circled in red. This table happens to be for Trenton. You can alternatively use the county data introduced in Module 1 for this storm, but we prefer the NOAA data server. So next we'll cover how the travel time for shallow concentrated flow is calculated. This travel time is equal to length for this particular segment divided by the estimated velocity and multiplied by 3600 for the conversion from seconds to hours. Velocity is estimated based on a site's surface condition and slope. So the value for the flow velocity can be determined from figure 15.4 of part 630 in the NEH. The velocities plotted are average values and are a function of watercourse slope and the cover condition of the channel. This source was derived by solving Manning's equation for a wider variety of different land covers. The y-axis is our slope in feet per feet. The x-axis is the average velocity in feet per second. So you would draw a horizontal line from your slope on the y-axis over to the condition line, and then draw a vertical line down to the x-axis to find your value for velocity. You may still see citations for a TR55 source, but remember that has been superseded. So make sure the graphical source used is the one shown here. So the last travel time we need to calculate is for open channel flow. For this calculation, we need the length of this segment, the roughness coefficient for the open channel flow, which is different from the other Manning's N value previously covered, hydraulic radius, and the channel slope. Manning's N values for open channel flow can be obtained from standard hydraulics textbooks. The hydraulic radius is equal to the cross-sectional flow area divided by the wetted perimeter, and that's the surface of the channel bottom and the sides that are in direct contact with the flow. Don't use this equation if you have flow under pressure in a pipe. That uses a different equation, and you shouldn't really see this type of flow that often in your stormwater calcs for development. So let's work through an example for calculating the time of concentration. So this says for the post-construction conditions, stormwater runoff flows through a wooded drainage area along a flow path measuring 1,000 feet in length, consisting of sheet flow over an area with a 0.5% slope and shallow concentrated flow over an area with a 1% slope. It's asking us to calculate the time of concentration, and this is for the post-construction condition. So a slope of 0.5% is equal to 0.005 feet per foot. And for woods, Manning's roughness coefficient for sheet flow in NJ is 0.4. Remember, that's the max. The sheet flow length is calculated by using the formula from the McEwen-Speece limitation criterion, since this is the post-construction condition. We previously obtained the 2-year rainfall depth, and so plugging this all into the equation shown yields a travel time of 9.18 minutes. So remember, the total flow path length is 1,000 feet, and since sheet flow segment length was calculated to be 17.68 feet, the length of the shallow concentrated flow segment must be the remainder, which is 982.32 feet. The value for the flow velocity can be determined from figure 15.4 mentioned earlier. And for this example, a horizontal line is projected across from the y-axis at the tick mark denoting the 1% slope to the curve representing the forested areas. And the corresponding velocity is 0.25 feet per second. And this value is then entered into the equation for the travel time for this segment. You get 65.5 minutes. And so our answer is the sum of the travel times for all the segments along the flow path. In this case, we have one sheet flow segment and one shallow concentrated flow segment, and the time summed to 74.7 minutes. Okay, next we'll discuss developing hydrographs, which we defined earlier as the graphs depicting the flow rate of runoff versus the time passed at a specific point of analysis. The hydrograph can provide much information about stormwater runoff, including the time of concentration, the time at which peak flow occurs, the peak flow rate, and the volume of runoff generated. So first we have to talk about the unitless and synthetic hydrographs for the NRCS methodology. A unit hydrograph is a direct runoff hydrograph resulting from 1 inch of excess rainfall. The unit hydrograph influences the shape of the runoff hydrograph, particularly the peak rate of discharge. Given a watershed's unit hydrograph, one can calculate the theoretical hydrograph for any storm event. In an ideal world, a unit hydrograph would be developed by meeting the flow from a watershed. Since this isn't very practicable, we use synthetic hydrographs instead. So 2 synthetic hydrographs were developed for determining runoff from watersheds. The 2 that we generally use are the SCS dimensionless unit hydrograph and the Delmarva dimensionless unit hydrograph. And most software packages have settings that allow selection of either of those. So first, let's talk about the SCS, which is based on an average of natural watersheds with various sizes and geographic locations, which allows to predict how an unmetered watershed will react to rainfall. It's important to note that within the state of New Jersey, the SCS unit hydrograph is used outside the coastal plain, except in rare circumstances. Shown here with an orange curve is the SCS unit hydrograph. The corresponding rainfall event is shaded in blue. As you can see, the timing of the hydrograph is based on the time of concentration on a site, which is highlighted in yellow. There is some runoff at the start of the event, and more areas up gradient of the point of analysis start to contribute. After the TC, the furthest away areas stop contributing and runoff continues to taper off. The volume of the runoff produced by the site in response to the rain event is equal to the area under the hydrograph. In development of this runoff hydrograph, the runoff discharge is nonlinear in relation to the time of the rain event in accordance with the NRCS observations from many natural unit hydrographs developed from various watersheds. The dimensionless unit hydrograph that was developed has a peak rate factor or a shape factor of 484, which means that 48.4% of the total runoff volume is discharged before the peak time, which is shaded in purple, and 51.6% of the total runoff is discharged after the peak time. The peak rate of runoff is the maximum height of the hydrograph here. You can usually see the shape factor on the printouts provided in stormwater reports. So that's another thing to check in your reviews. The second commonly used dimensionless unit hydrograph is the Delmarva unit hydrograph. The Delmarva hydrograph is suited for the flat coastal areas in Delaware, Maryland, and Virginia, which is where it's got its name, but it's also applicable to those same areas in New Jersey. So shown here is a comparison of the SCS and Delmarva unit hydrographs. When calculating the peak flow using the Delmarva hydrograph, we use a constant shape factor that is lower than that for the SCS unit hydrograph. So if we broke down each individual equation to develop the Delmarva, its shape factor is around 284 or 285, depending on the software used. The Delmarva unit hydrograph will not affect the determination of runoff volume, but should result in a lower peak discharge when compared to the SCS unit hydrograph. The lower shape factor for the Delmarva means there's less volume under the rising limb, so the hydrograph is a bit shorter in height, but it's also longer in duration. And this comes in part to the from the general slope of the terrain and the lower level of urbanization and so forth. The Delmarva DUH must be used in calculating pre-construction and post-construction peak flow rates for the 210 and 100-year storms in the coastal plain region of New Jersey, except in very specific circumstances, which we'll cover in a few slides. Also note that if the Delmarva is used in the precondition, it must be used in the postcondition. That's likewise for the SCS. Projects which lie on or near the boundary between the Piedmont and coastal plain regions should be modeled with both the standard and Delmarva unit hydrographs and results compared with actual field conditions to determine which unit hydrograph offers a best fit. So where's that boundary exactly? This is just a zoomed in view with a few points of interest added to that same map you saw on the previous slide. The blue line dividing the state is the boundary of the coastal plain. The hyperlink here in the header is to the Bureau of Geologic Information Systems for more information, and the other link below the image is to get the shapefile data for GIS users. You want to be careful in outlying parts of locations near the border of the coastal plain. For example, parts of Princeton and Monmouth Junctions, a little bit northwest of Trenton. Those are just to name a few. The lower GIS length is probably your best bet with being able to determine exactly where your site is. Alternatively, the Municipal Stormwater Management Plan may include this information as well. So when not to use the Delmarva dimensionless unit hydrograph, the Delmarva DUH must not be used outside the coastal plain of New Jersey. For another instance, use of the Delmarva unit hydrograph is not allowed when sizing manufactured treatment devices because it will underestimate the flow rates. And lastly, when a site is within the coastal plain and the design engineer can prove to the satisfaction of the review engineer that the conditions for applicability of the Delmarva unit hydrograph are in no way present anywhere in the watershed. For example, if the site is completely paved, or there are very, very steep slopes, such as slopes maybe greater than 10%. In addition to the rainfall depth data, we have to know how rain falls during a storm event if we are going to create models and design BMPs to address runoff. To achieve the goal of estimating rainfall event for design and planning purposes between 1961 and 1977, NRCS developed synthetic rainfall distributions from historical records for the different regions of the country. And the basic shape of the distributions all assume rain starts gently, increases in intensity, and then tapers off. The type 3 distribution was previously used for about 20 years. Now we require use of either the NOAA C or D distribution, depending on which county we are in, per the 2012 bulletin from NRCS. One of our coworkers has done some modeling using these, and we have learned that you can expect to see slightly higher peak flow rates when using the C and D distributions as compared to the previous type 3. So here's the map of the state depicting the regions. You can see the darker shaded counties will use the NOAA C distribution, while the other counties use the NOAA D distribution. And you should be able to download text data using this hyperlink here. We've also added a link to make this information available as an Excel file from our DEP webpage. Okay, the next objective, an important approach to managing stormwater runoff is new impervious cover that is not directly connected to a site's drainage system. So this is now extra important with GI requirements of the rule. Again, if you have any questions, you can type them into the chat, and our staff will do their best to respond. I know this is kind of a long presentation. So to slow down runoff generated by impervious surfaces, certain key aspects must be addressed. Runoff from unconnected impervious areas must undergo sheet flow onto adjacent pervious areas, where a portion of the impervious area runoff is given an opportunity to infiltrate into the soil without causing erosion and further sediment transport to whatever is down gradient. Under certain conditions, this technique can help in providing both groundwater recharge and stormwater quality treatment for small rainfall events, as well as reduce the overall runoff volume that must be treated and or controlled in a down gradient BMP. So there are 5 conditions that must be met for an impervious area to be considered as an unconnected impervious area. Here are the first 2 conditions. And basically, the runoff must enter the pervious area as sheet flow, and it must remain that way. And the other 3 conditions ensure the stability and maintain the sheet flow. For this reason, there is a limit on the steepness of the slope to 8% in the down gradient impervious area. So there are 2 methods that may be used to calculate runoff from unconnected impervious areas, and there are 3 additional requirements applicable to either method. They're listed here. So the 2 methods are the NRCS composite CN with unconnected impervious from Chapter 9 in the NEH, and which has a 30% limitation on the impervious to the combination of impervious surface and the receiving pervious surfaces. And then there's the NJDEP 2-step method, and that's the one we'll cover now. So as an example of the 2-step method, we've got sheet flow over the impervious surface of 25 feet. And that doesn't exceed the maximum allowed flow path length. That was one of the criteria that we saw on a previous slide. And we have 75 feet of sheet flow over the down gradient impervious area, which meets the minimum requirement of 25 feet. We use the NRCS runoff equation from earlier to compute the volume generated by the impervious area, and which comes out to 1362.5 cubic feet. And the next step is to assume this runoff is evenly distributed as rainfall falling over the adjacent pervious surface. So to begin that step, we take the runoff volume produced by the design storm falling onto the impervious area, in this case the 2-year storm, and we divide that previously calculated volume by the area of the down gradient impervious surface to get rainfall depth and converting units as necessary. We then take that rainfall depth and add it to the 2-year storm rainfall depth, which also falls onto the pervious surface, to get the total effective rainfall depth of 4.59 inches. Now we can use the NRCS equation for the pervious area, inputting this total effective rainfall depth and the appropriate on-site retention S to get the effective depth of rain falling on the pervious area. And we can convert that effective depth to effective volume by multiplying back by the pervious area. And we see 156 cubic feet. It's a pretty good amount of reduction in volume. So before we get into a discussion of the rational method, we should briefly go over some of the other updates to our BMP manual chapter 5. So there's quite a bit of material on these next slides. So you definitely will want to read through chapter 5 on your own, as this will only be a brief overview. So here are the first requirements for using exfiltration in routing calculations as listed on pages 7 and 8 of chapter 5. Exfiltration is only allowed for certain small-scale GI BMPs that infiltrate runoff. All soil testing must follow Chapter 12 requirements, which will be further discussed in the next presentation. Also, all design criteria as provided in the respective chapter of the BMP manual must be followed before the BMP can be approved, and pre-treatment must be included unless otherwise so stated in the BMP manual. An exception for that would be for those really small scale BMPs where the drainage areas are less than or equal to an acre. So now we can talk a little bit about the pre-treatment requirement, because that extends beyond just being a requirement for using exfiltration in the routing computations. So each of the subchapters in Chapter 9 were revised. Chapter 9 is now the BMPs that are small in scale and also meet the definition of green infrastructure or GI because they allow stormwater to be treated through vegetation or soil, provide for reuse or infiltrate runoff into the soil. There are BMPs in Chapter 10, which are also GI, but are larger in scale and only used to meet the stormwater runoff quantity requirement. Their use and limitations are detailed in the summary on their respective chapter cover page. And they're also listed in Table 5.2 of the rules. And finally, there are the BMPs in Chapter 11, and they're not GI. Accordingly, pretreatment is an important design criteria. If you do not see pretreatment listed under the basic design criteria for a particular BMP, it's under the type-specific design criteria. Roof runoff can be treated by certain measures listed here and on the pages listed in the bulleted text. Here are some graphics taken from Chapter 9.1 showing the devices that can be used to pre-treat roof runoff. The requirement for pre-treatment of roof runoff can be waived under the conditions listed here. For example, a building that is significantly taller than any surrounding trees and doesn't have a vegetative roof should not need the pre-treatment. However, in making this determination, the review agency must consider the mature height of any surrounding trees. When using another BMP for pre-treatment, it must be designed in accordance with the design requirements outlined in its respective chapter. Always check the BMP manual for the specifics. Roof runoff that is commingled with surface generated runoff must be treated per the manual. For subsurface infiltration basins, pre-treatment may consist of any of the BMPs found in the manual, and 80% TSS removal by the pre-treatment is required. Small-scale bioretention systems designed to infiltrate that have flow entering a sheet or overland flow may alternatively use a 5-foot wide gravel or stone strip to filter runoff instead of other forms of pretreatment. So back to the requirements for using exfiltration. Where can't you use exfiltration? Exfiltration cannot be used with any under-drained BMPs because exfiltration is removing runoff volume from the system, and under-drains don't allow for that. Also, for those sites in special areas or that have no runoff leaving the site in the pre-construction condition, exfiltration can be used for an entire storm under these conditions. You must determine which is the maximum storm for which no runoff leaves the site in the existing condition, or if infiltration of the entire storm is required by a law or rule established by the Pinelands Commission, the Highlands Council, or other stormwater review agency that has jurisdiction over the project. Groundwater mounding analyses are required when using exfiltration in the routings. These are the conditions that also apply. Basically, soils must be tested in accordance with Chapter 12, and you must follow Chapter 13, which is specifically about the groundwater mounding analysis method to be used. So here are some additional things you need to know about groundwater mounding. The groundwater mounding analysis has determined that an adverse impact will occur if the resulting groundwater mound reaches the bottom of the BMP, or if the temporary localized increase in the water table encroaches upon a building or another subsurface structure, including any septic systems. So be careful of that. We've seen some issues with septic systems before. When an adverse impact is the result, further modifications to the size of the infiltration area of the B&P or reductions in the exfiltration rate must be performed until the adverse impacts are eliminated. A groundwater mound that reaches the bottom of the B&P means the hydraulic gradient is reduced, which is another way of saying that the B&P cannot infiltrate runoff as fast as originally expected. So you'll have to redo the routing calculations to calculate new peak flow rates. We won't run through it here, but you can refer to Chapter 5 of the B&P manual for the methodology to be used, specifically examples 5.6 and 5.7, which begin on page 44. Groundwater mounding is itself a presentation in Module 3, so we'll take an in-depth look later on as we go through the examples there. So this is just like a cursory overview. Meanwhile, though, we have to finish up on the calculations and methods covered in Chapter 5. So now we'll move on to covering use of the rational method because it's still a method noted in the rules. So again, the rational method has been around a long time, since 1889. It's a simplified method, and how it should be used is based on certain assumptions. One assumption is that the rainfall intensity is the same everywhere in a drainage area for the duration of that particular rainfall event. Almost everything is assumed to be uniform, such as ground cover, soil type, and slope. You should always check that this assumption is valid. This is something often oversimplified. Secondly, the maximum runoff rate occurs when the rainfall duration lasts as long as the time of concentration, meaning every point in the drainage area is contributing runoff. And lastly, the frequency of rainfall and runoff are equal, meaning a 2-year storm will generate a 2-year flow, assuming everything is equal and constant throughout the entire drainage area. So the B&P manual says use of the rational method should be limited to drainage areas less than 20 acres with uniform surface cover, soil type, and slope. It's typically used for urban areas. It's not applicable if areas of ponding occur within the drainage basin. And this method is used only to calculate peak flow rates. It can't calculate any volumes. So the rational method equation is Q equals CIA, and again, can only determine the peak flow rate. Q is the peak flow in CFS. C is a dimensionless runoff coefficient, for which can be found in table 5.3 from the B&P manual chapter 5. I is the intensity in inches per hour, and A is the area in acres. So note that the rational equation may not appear to be dimensionally correct, in that although I is specified in inches per hour, 1 inch per hour equals 1.008 CFS per acre. But in using this equation, the two are taken to be numerically equal, so no conversion factors are required. One source for a comprehensive table of runoff coefficients is table 5.3 of the new version of chapter 5. The rational runoff coefficient relates the percentage of rainfall that will become runoff. As was mentioned in module 1, less runoff is produced by forest than pavement with the same slope. And we recommend using a value of 0.99 for impervious surfaces, as this is conservative and will best represent what will actually occur. Sometimes you might see a C of 0.95, and that can make a difference. We also calculate the time of concentration in the same way as for the NRCS methodology. So next we need to determine the rainfall intensity. And when you're reviewing calculations using the rational method, check the rainfall data on the NOAA data server and make sure you have the intensity tab checked rather than the depth tab. So shown here is data for the NJDP headquarters in Trenton, and we've assumed a 2-year storm with a time of concentration of 10 minutes to get 3.92 inches per hour for the 2-year design storm. So, or you could also use the IDF curves shown from the NOAA data. For stormwater calculations, the rainfall intensity is the average rainfall rate for a duration equal to the time of concentration, subject to the minimum time of concentration for a selected rainfall event. Once the recurrence interval has been selected for the design, excuse me, and a time of concentration calculated for the drainage area, the rainfall intensity can be determined from the IDF curves. And Chapter 5 includes additional guidance on obtaining this rainfall intensity information. Identifying the proper duration and intensity to be used for design purposes is very important. So just to repeat, the rational method calculates only the peak flow rate for a specific storm event and not runoff volume. The rational method is often used in sizing manufactured treatment devices based on peak flow rate. For the New Jersey Water Quality Design Storm, the rainfall distribution for this storm event is not evenly distributed over the entire duration. Therefore, using an average intensity of 1.25 inches over 2 hours or 0.625 inches per hour, which we see pretty frequently, cannot be used as the value for rainfall intensity in the rational method equation. When using the rational method, the minimum time of concentration that may be used is 10 minutes. And for the water quality design storm, the corresponding intensity is 3.2 inches per hour, not the 0.625 inches per hour. So make sure that the correct intensity is used in sizing your MTDs, and this will be covered further in the next module. So if you haven't read it, Chapter 13 includes many more groundwater mounting examples. Even our Chapter 5 includes examples with groundwater mounting analysis and using exfiltration in the routings. So take a look at those. Thank you. Up next should be Lisa Schaefer.
Hi, everyone. It's Lisa. I wanted to check with our moderator if we have time for a break.
Yes, please take a 5 minutes break and we will come back.
Yeah, how are you?
Hello, everyone. It's 2 o'clock. Moderator, is it time to start? Okay. All right. Hi, I'm Lisa Schaefer. I'm another one of the environmental engineers in the Municipal Stormwater Engineering Unit, and I'll be presenting the soil testing requirements. Hopefully I won't go through this too quickly, but let's see. You could turn on live captions. The others will help you if you need to do that. But with that, I'm going to get started. So understanding the character and saturated hydraulic conductivity of surface and subsurface soils at a proposed land development site is crucial to the design of stormwater BMPs that meet the requirements of the stormwater management rules. I'll be going over the soil testing requirements and what is to be submitted with regards to soil testing in the stormwater management report for a major development project. Now, if you're still using Appendix E from the older versions of the BMP manual, take note, it's been updated, it's been published, it's Chapter 12 now, and I hope that you'll start using that. So before I go further, it's also to mention that as part of our audit experience, soil testing has been one of the areas that we often found was done incorrectly. So this presentation will cover the information that is presented in Chapter 12, and that includes why we need to do soil testing, determining HSG or hydrologic soil group, the soil testing for infiltration BMPs, those testing that is done to determine the location of the seasonal high water table, as well as the soil testing requirements for construction and post-construction parts of the rule, and also what information is to be submitted in a soil testing report. So there's a misconception that soil testing is required only when an infiltration BMP is proposed. And actually, soil testing is just so much more than determining the saturated soil hydraulic conductivity. Soil testing also includes finding the hydrologic soil group, as I just mentioned, determining the location of the seasonal high water table, and the soil series present on a site. The identification of the correct HSG is essential to performing accurate calculations for the volume and peak flow rate of runoff, regardless of the BMP being designed. Also, many BMPs require separation between the bottom of the BMP and the seasonal high water table. So, for example, in a small-scale infiltration basin, the 2-foot separation from the seasonal high water table should be measured from the bottom of the sand layer. For a large-scale bioretention system with underdrain, look at page 11 of Chapter 10.1, where it specifies the seasonal high water table must be at least 1 foot below the bottom of the gravel layer, inside which is the underdrain pipe itself, and that is sitting on at least 3 inches of gravel. So if there's no soil testing report showing the depth of the seasonal high water table, the reviewer is not able to judge if this design criteria has been met. Furthermore, when you're using the groundwater recharge spreadsheet to calculate the annual groundwater recharge and, of course, the deficit, you'll need to know not only the HSG, but the soil series present. All right, details on this will also be included in Module 3. So the first topic today is the determination of HSG, and that's used in the selection of the runoff curve number, or CN, that is developed by the National Resource Conservation Service, or NRCS. And there are three methods used to determine the HSG. One is the NRCS Web Soil Survey. The link is here. Then I'll go through the default method, and then I'll go through the HSG testing procedures that are from subsection 1C in Chapter 12. So before we go through each of these methods, we're going to touch on using the old paper versions from the county soil surveys. Now, we checked with the NRCS, and they indicated that they're no longer updating these old documents. The NRCS also indicated the web soil surveys contain the most up-to-date information. So therefore, we are requesting that paper-based information be verified with the web soil survey. So that means the web soil survey is the first source to be consulted for the HSG information before going to the second or third method. And so, by the way, I want you to know that the NRCS has soil maps and data for about 95% of the nation's counties. So the web soil survey itself is fairly user-friendly, and it makes it pretty easy to check the accuracy of the information you receive as a reviewer. And now, if this information is omitted from the submittal packet, knowing how to get the soil survey allows you as the reviewer continuing to check the parameters used in the stormwater calculations while you wait for them to get their ducks in a row. Okay, so to get started, once you're on the NRCS Web Soil Survey website, just click on the green Start WSS button. All right, and after clicking that button, you're going to begin zooming into the area of interest, or AOI, and it's the tab circled in red on the left, and either zoom in to the project location using the icons in the yellow oval, or click on an address by the green arrow that I've superimposed and then enter in the address. Then you're going to use the AOI icons in the turquoise oval to either draw a rectangle or a polygon around the site. I like to check the accuracy of my polygon against a property survey to check that I got the entire property. The area of information will appear under the AOI Properties pull-down menu that's on the left of the screen above the quick navigation menu bar. All right, then the next tab that you will click is on the Soil Data Explorer, which is one of the yellowish tabs that's within the blue oval. Next, select the tab labeled Soil Properties and Qualities, which is the new red oval, and click on the pull-down menu for the item labeled Soil Qualities and Features next to the arrow that popped up a little early. Then you're going to scroll down to find the hydrologic soil group, which is the brownish bar inside that turquoise oval. All right. So clicking on the pull-down menu for HSG will allow you to select the View Rating button, and it's circled inside this new red oval. You'll then see a table that's listing the HSG for the soils within the selected area, listed by soil mapping unit, and this table's the white area that just popped up on your screen on the bottom right. The top row that you see here is Fort Mott Loamy Sand, which has a rating of A and covers the area shown on the right side of the table over here. Okay, the second row is Galloway Loamy Sand, and we see a double rating on in the table. So for soils with a dual HSG rating, such as A/D, B/D, or C/D, the first letter is going to apply to the drain condition, and the second applies to the undrained condition. The appropriate choice of HSG would depend on whether or not the site has been drained, of course. So further investigation is necessary, and I'll be discussing this in a little bit. All right, so moving down the table, we get to where I've superimposed a light greenish, where's it? Yeah, there it is, rectangle on the two areas for which there's no rating over here. Okay, these rows correspond to the two areas of the graphic inside the dashed red ovals, all right, and they're filled also with that grayish green color. So keep in mind that when there's no rating, other steps will have to be taken. A lack of a rating often happens in urban areas where the soil might have been disturbed or the area has been filled with construction materials. So for those instances where there is no HSG rating, the soils in the undetermined area and the soil series may be determined by the other two methods that I'll discuss shortly. And those are the default method and the procedures identified in subsection 1C from chapter 12. Now, one thing I would like to note is that if it's known that the site has been filled with construction materials, debris, or other material than the soil shown in the soil survey map, you're not going to solely rely on the HSG information shown in the web soil survey. You'll have to use the other methods to determine the hydrologic soil group. So where HSG information from the soil survey is unavailable, default HSGs may be used for runoff computations for pre and post development conditions. So as we mentioned, the HSGs in urban areas are often unknown. So this is usually where we use the default values. So when we're in the coastal plain, the pre-developed condition HSG to be used is A, with HSG D used for the post-developed condition. Outside the coastal plain, HSGB is used for pre-developed conditions, and again, HSGD is used for post-developed or post-construction conditions, however you like to call it. Now, on the right is the map of the physiographic provinces of New Jersey, showing where the coastal plain is found, and you saw this in an earlier presentation. And if you click on the link at the bottom of the slide, that's going to take you to the Bureau of GIS for a new interactive website. And what's really cool about this is that you can enter a location to find out in which province an address is located. And here's what the site looks like when you first are zoomed out. The page is very interactive, and you can zoom in enough to differentiate between two houses on a street. For example, here's 401 East State Street next to the green arrow that I pasted on top, and we see that the site is in the Piedmont province. The lighter blue area at the bottom down here is where the coastal plain is located, and I think you'll really appreciate how easy it is now to check whether a project is in the coastal plain. So if you don't want to use the default values, then you have to go to the soil testing. And the assignment of HSG is determined by the water transmitting soil layer with the lowest saturated hydraulic conductivity and depth to any layer that is more or less water impermeable, such as fragipan or doorpan, or depth to a water table if present. The least transmissive layer can be any soil horizon that transmits water at a slower rate relative to those horizons above or below it. Table 7-1 in Chapter 7 of the NRCS National Engineering Handbook, Part 630 for hydrology, is where the list for the criteria for assignment of HSG can be found. You're going to take note that older versions of this presentation may have used a different link, so you can share that information with your coworkers. So this on the right is Table 7-1 from the NEH, and the title is Criteria for Assignment of Hydrologic Soil Group, or HSG, and it relates saturated hydraulic conductivity to hydrologic soil group, and it's determined by a couple of things: depth to a water impermeable soil layer that has a saturated hydraulic conductivity of 0.1 inches per hour or less, depth to the seasonal high water table, and saturated hydraulic conductivity of the most restrictive soil layer within the depth to a water impermeable layer. Now, I do have to read to you a certain part from Chapter 7. Certain wet soils are placed in Group D based solely on the presence of a water table within 24 inches of the surface, even though saturated hydraulic conductivity may be favorable for water transmission. If these soils can be adequately drained, then they are assigned to dual hydrologic soil groups, A/D, B/D, and C/D based on their saturated hydraulic conductivity and the water table depth when drained. The first letter applies to the drain condition and the second to the undrained condition. For the purpose of hydrologic soil group, adequately drained means that the seasonal high water table is kept at least 24 inches below the surface in a soil where it would be higher in a natural state. So if the depth is less than 20 inches, the soil is classified as D, and that's per the top row in the table. Where the depth to the water impermeable layer is 20 to 40 inches, we would look in this table in the area of the red oval. Then, if the depth to the high water table is less than 24, we look to the right of the orange oval. Next, we find the saturated hydraulic conductivity range for the least transmissive layer within the corresponding depth range, and the HSG designation is what you would see in the right-hand column. So, continuing on to the test procedures, the presence and depth of the restrictions must be included in the soil logs for each soil profile pit and boring. On the left is a soil sample log showing the depth to the restrictive layer, and the seasonal high water table is also shown here by the blue line. On the right is a shallow soil pit. It has a face that's been cleaned and prepared for describing the soil profile. This particular one is from Alaska, and it was actually only dug to a depth of the permafrost around 15 inches. So moving on. Next is the required number of soil profile pits and soil borings that are required for soil testing to determine HSG. So for each soil mapping unit that is less than 0.5 acres, 1 pit and 1 boring are required. We're going to go across, okay? For each soil mapping unit between 0.5 and 2 acres, 1 pit and 4 borings are required. And then for each soil mapping unit greater than 2 acres, 1 pit plus 1 pit per each additional 2 acres, and 4 borings plus 2 more borings per each additional 2 acres are required. So the placement is also an important part of the requirement. The soil profile pits and borings should be completed equidistant apart within the boundaries of the mapping unit to provide adequate characterization. So we're going to look at 2 examples. One is going to be over there on the left. So the pink area, it's 2 acres in size, and we see 1 soil profile pit and 4 borings. Those meet the criteria. Now, moving over to the right for the 6-acre area that's shown all with the 3 green areas, we see 3 pits and 8 borings. That's 1 soil profile pit and 4 borings for the first 2 acres, and then 1 soil pit and 2 borings for the next 2 acres, and so forth. And this also meets the placement requirement. Now, besides placement, there's also a depth aspect to the requirements. And I want you to take note that the soil profile and boring depth requirements have been updated in Chapter 12. Previously, we had a depth of 6 feet as the requirement, but now we need at least 40 inches. The presence and depth of soil classification must be included in the soil logs. Okay, so that basically is everything I have for you today on determining the HSG, but there's a workbook that you can download from the website, and this is the first workbook in the whole shebang, and that will give you a place to record your findings. Okay. Next I'm going to cover the soil testing requirements for infiltration BMPs. That's what's found in section 2 of chapter 12. So first of all, by infiltration BMPs, we mean a BMP that infiltrates runoff into subsoils, and that includes the BMPs such as infiltration basins, along with sand filters, bioretention basins, and pervious paving systems designed without an underdrain. Testing for BMPs with underdrains will be discussed later. All right, so let's first look at the number of soil profile pits and soil boring requirements for any infiltration BMP. Obviously, knowing where the seasonal high water table is located is essential, and a minimum of 2 soil profile pits must be excavated within the infiltration area of any proposed infiltration BMP to determine the elevation of the seasonal high water table and to test the hydraulic conductivity of the most restrictive horizon between the basin bottom and the seasonal high water table. Now, placement of the test pits must be sufficient to provide adequate characterization of the infiltration area. And for BMP infiltration areas that are larger than 10,000 feet, a minimum of 1 additional soil profile pit must be conducted for each additional area of 10,000 square feet. Now, at least 1 test to establish soil hydraulic conductivity must be conducted for each soil profile pit. And to verify the location and numbers of the soil profile pits, you'll need to see a site plan depicting the locations of these soil profile pits that are within the infiltration area of the proposed BMP. So this is an example of the soil profile pits for an infiltration BMP with a bottom or infiltration area measuring 100 feet by 250 feet. So for our 25,000 square foot infiltration basin, we need 2 profile pits for the first 10,000 square feet, plus 1 for the additional 10,000 square feet in the middle section, okay, plus 1 more for that extra 5,000 square feet on the right end. All right, now let's talk about when we have small scale infiltration BMPs. So when we have 1 or more infiltration BMPs that are the small scale GI or dry wells, we need 1 soil profile pit for each soil mapping unit where the multiple BMPs are located, plus for each BMP with an infiltration area less than or equal to 500 square feet, we're going to need 1 soil boring at each BMP. Now, for each BMP with an infiltration area greater than 500 square feet, we're going to need 2 soil borings at each BMP. And for our small-scale GI BMPs arranged linearly, we're going to have 1 soil boring at each BMP and 1 soil profile pit for every 2,000 feet of length. All right, now I've gone through this rather quickly. This information is currently found on pages 13 and 14 of chapter 12, should you need to refer back to it, or if you're, like me and you want to check everything out. All right, so let's talk about the linear infiltration BMPs. And to be one, you have to meet all 3 of the bulleted criteria. And this is the information that's also found on page 15 of chapter 12. So for linear infiltration BMPs, a minimum of 1 soil profile pit must be conducted within each soil mapping unit. And in each soil mapping unit, the soil profile pit must be conducted within the first 500 linear feet of the BMP. If the linear BMP exceeds 500 feet in length, 1 soil boring must be conducted at every 500-foot interval, and 1 additional soil profile pit must be conducted for every 2,000 linear feet. All soil explorations must be equidistant to adequately characterize the infiltration area. All right, so let's do an example or 2 for linear infiltration BMPs. All right, we're going to have 2 sites. The first is shown on the top half of the slide, and it has 2 soil mapping units. All right, we include 1 pit for a linear BMP 500 feet in length that's shown in the soil mapping unit represented by yellow. And next is 1 pit for the first 500 linear feet of the soil mapping unit represented by the green. So we're up here on the slide with 1 boring for each additional 500 linear feet portion. Okay, so that would meet the criteria. Now for the second or the bottom half of this slide, there's a linear infiltration BMP with a total length. It's 2,500 feet in length. All right, all within 1 soil mapping unit. So what's needed is the required pit for the first 500 linear feet, and then 1 boring for at each 500-foot increment, plus 1 more pit because we're now over 2,000 linear feet after the first 500 feet that was covered by the initial pit. Okay, all right. Now, let's move on to the test to determine soil hydraulic conductivity. And so the following requirements are for the scenario in which no soil replacement is proposed. Hold on one second. After determining the numbers and locations of the soil profile pits for infiltration BMPs, you're going to have to decide the length of the soil, the depth of the soil profile pit and which soil layer to select for performing the test for soil hydraulic conductivity. So it must be in the most hydraulically restrictive horizon or substratum above the seasonal high water table or your non-fractured bedrock, but located below the lowest elevation of a BMP and above whichever of the following depths is greater, either 8 feet below the lowest elevation of the BMP or to a depth that is equal to twice the maximum potential water depth in the BMP measured from the lowest elevation of the BMP. Now, if soil replacement is proposed beyond the required layers in the BMP, the depth is measured from the elevation of the bottom of the required sand or soil layer. So this requirement means first, the excavation of the soil profile must reach to the required depth, and second, the hydraulic conductivity must be tested on the most hydraulically restricted soil layer below the soil replacement or the lowest point of the basin, but above the required soil profile depth. So please note that the depth requirement of whichever is greater, that is 8 feet or twice the maximum water depth, it's measured from the lowest point of the basin bottom or from the bottom of the soil replacement. Now, quite often we've seen the test is performed at the depth to where the soils are to be excavated, but that is the wrong place to do this. So please be sure to check this in your reviews. All right, up next is a discussion of what test methods are acceptable. Soil hydraulic conductivity can be determined using a tube permeameter test, a percolation test, a single ring infiltration test, a basin flooding test, or a modified basin flooding test. You're going to read the specific conditions that are published in Chapter 12 for which these tests that can be used. Additional methods of establishing the soil hydraulic conductivity, such as ASTM D3385, the double ring infiltrometer, and USBR 7300-89, the well permeameter method, or other soil hydraulic conductivity tests that use in situ conditions and are accompanied by a recognized published source reference can be used, such as the Guelph permeameter, I apologize if I'm saying that wrong, the Philip Dunn permeameter available at the Soil Science Society of America book series, Methods of Soil Analysis Part 1. It's in the document called Physical and Mineralogical Methods by Clute. It's dated 1986. Okay, you'll find all of this information in Chapter 12, as I said. All right. So when you're performing a soil boring during the soil exploration, the soil borings must be performed and reported in accordance with ASTM D1452, Practice for Soil Investigation and Sampling Auger Borings, and ASTM D1586, Test Method for Penetration Test and Split Barrel Sampling of Soils. Sampling must be continuous for the entire depth of the soil boring to fully characterize the soil profile. Okay, since the actual saturated hydraulic conductivity rate may vary from the soil testing results and may decrease over time, a factor of safety of 2 must be applied to the slowest tested saturated hydraulic conductivity rate to determine the design saturated hydraulic conductivity rate. Okay, that is what is then used to compute a BMP's drain time for the maximum design volume, the exfiltration rate for a BMP allowing exfiltration in the routing calculation, or the infiltration rate in the groundwater mounding analysis. Now, where any tested saturated hydraulic conductivity rate is 20 inches an hour or more, the maximum designed saturated hydraulic conductivity rate that can be used is 10 inches per hour. Okay, the test procedures and the conversion equations for the test shown here, sorry, you'll see that on the next slide, are available in Chapter 12 of the BMP manual. And there are also worksheets for some of these. All right, the case borehole method is suspended temporarily for further assessment, but don't use this test. But we do have everything else here in subsections A1, A2, 3, 4, and 5. Now, for the double ring infiltrometer, the well permeameter, and other permitted testing methods, you can obtain them from the American Society for Testing and Materials, or the organization, of course, that's publishing the test method. For the PERC test, follow the procedures that are described in Chapter 12, and the field measured hydraulic conductivity value shall be calculated using this simplified equation, and that's also in Chapter 12. All right, you want to take note that although the test step B in the test procedure for a PERC test requires you to fill the water to a depth of 7 inches, the time of recording started once the water level drops to 6 inches and then is stopped when the water in the hole has emptied. The second worksheet in the Excel workbook may be helpful for your hydraulic conductivity testing. I've just split it into two parts here. The left is the top and middle, and the right is the lower part of that worksheet. Okay, but this is what it looks like if you haven't seen it before. All right, so next is soil testing to determine the seasonal high water table, which obviously we abbreviate a lot in our text as SHWT. So pursuant, well, you're going to see some stuff in Table 5.1 in the rules where testing is not applicable to BMPs such as blue and green roofs. Because they're constructed as above grade BMPs. And there are others listed there where there's no separation listed in the table. All right, but testing is still required for BMPs with under drains, grass swales, and BMPs designed to infiltrate. Okay, this section of the chapter, all right, never stated that under drain BMPs were excluded. So that's why we're clarifying this issue. Okay, so for your BMPs designed to infiltrate, you're going to follow items A and B. And then for your non-infiltration BMPs, you're going to test the area that's going to be occupied by the BMP. And you're actually going to use the requirements for infiltration BMPs to help you establish the number of tests required. Now, if you're getting inconsistent results in your tests or see inconsistencies when reviewing the soil testing data, then depending on your case, you're either going to perform or you're going to require more testing to resolve those discrepancies. All right, so when you set out to determine the location of the seasonal high water table, basically you're using your visual observations to help you decide where what part of this requirement you fall into. All right, so where the reduxomorphic features such as modeling are observed and it's any time of the year, then you're going to take the seasonal high water table to be located at the highest level at which those reduxomorphic features are observed, except when the water table is observed at a level higher than the level of the reduxomorphic depletions or concentrations. Okay. Details on determining whether saturated soils are present can be read in the guidance document published by the NRCS, Field Indicators of Hydric Soils in the United States. So you may find that helpful. All right, but if you've gone out and you're not seeing modeling, all right, you have, well, during the months of January through April, water levels may be measured directly within the soil profile pits or borings. All right, and when the department determines that there's been a significant departure from normal climatic conditions, the department may, with due notice to the administrative authority, it can lengthen or shorten the period allowed for direct measurement at any given year or in any given year. In low-lying coastal areas where the groundwater levels fluctuate with the tides, measurements shall be taken at the time of highest groundwater elevation in response to tidal fluctuation. But I want you to note that so far there's been no such change in the time frame for direct observation. Now, during other times of the year, the depth of the seasonal high water table is obtained from the Soil Conservation Service web soil survey, provided that the soil series present at the site is identified based on a comparison of the soil profile morphology observed within a soil profile pit and the soil profile description provided for the soil series in question within the web soil survey. So in cases where the seasonal high water table is shown as a range of elevations in the web soil survey, you're going to use the highest elevation of the range as a location of the seasonal high water table. So basically, those are the covers pretty much everything in terms of modeling, not modeling, and what times of year. And I know it's always confusing. Okay, but we're going to move on. And before I do that, I want to show you the third worksheet that you can use to record your observations or to review the observations reported. All right. So the next part of our presentation covers the construction and post-construction oversight testing requirements. So during construction, regular oversight must be provided by the professional engineer to establish that the basin is going to function as designed. And oversight includes, but is not limited to, a pre-construction meeting with the contractor, confirmation of the proper use of construction equipment, especially to minimize compaction of the infiltration area. Also ensuring that earthwork does not occur within the BMP area when the soil moisture content is above the lower plastic limit, and that the specifications of any replacement soils is or are met as the case may be. Ensuring that proper precautions are taken to prevent sediment entering the infiltration area during construction or where unavoidable. If the basin is used as a sedimentation basin, excavation for the sediment basin is at least 2 feet above the final design elevation of the basin bottom. Okay, post-construction soil hydraulic conductivity tests must be conducted to ensure that the installed BMP functions as designed. This is part of the design criteria in many of the subchapters of the BMP manual. Such testing must be carefully undertaken when all BMP construction that may affect soil hydraulic conductivity has been completed, and this includes the use of all construction equipment and the placement of all construction material that may affect soil hydraulic conductivity. In addition, hand tools and manual permeability test procedures must be used to avoid affecting the soil hydraulic conductivity. The required number of tests for post-construction testing are as follows. The number of soil hydraulic conductivity tests must follow the same requirements as the requirements for pre-construction soil hydraulic conductivity tests, and as for the required test depth, the post-construction hydraulic conductivity test must be conducted at the bottom of the excavation of the BMP before the sand layer or soil bed is placed into the BMP. The permitted test methods for post-construction testing are as follows. Only the single ring infiltration test, the basin flooding test, and the double ring infiltration test are a similar test that does not require a test hole in the soil layer are allowed. The tested soil hydraulic conductivity from the post-construction test must be equal or greater than the tested soil hydraulic conductivity of the most restrictive soil layer that was tested in the pre-construction condition. And lastly, all post-construction soil hydraulic conductivity test results must be certified by a licensed professional engineer, submitted to the review agency, and recorded in the as-built documents. This is also something that we didn't always see in our audits. All right, so far I've covered the requirements for soil testing to provide information on HSG to determine the runoff from a site, for saturated hydraulic conductivity that determines the permeability of the soil underneath the basin, and for the seasonal high water table that determines if the BMP can be drained at all. Therefore, I hope you agree that soil testing results are an essential part of the stormwater management design. Furthermore, since exfiltration is allowed now in the routing calculations for infiltration BMPs, the volume and flow rate of runoff that can be actually infiltrated into the subsoil will affect the sizing of the BMP and, of course, the outlet structures. So more than ever, soil testing results that correctly describe the soil characteristics are really, really important. All right, so now what we're going to do is address what's required for submittal with the stormwater management report. And the reviewer should check that the following is included: your web soil survey showing the HSG, the location of your soil profile pits and/or your soil borings. And in your soil test logs, you're going to want to see the date that everything was done, the elevation of the existing ground level, the depth of the soil profile or boring. And of course, you're going to check that to make sure it was done to the appropriate depth. Your soil classifications and descriptions, depth of the soil where the saturated soil hydraulic conductivity test is performed, okay, observation of soil modeling showing your redoxomorphic features or groundwater observations that identify where the seasonal high water table is located, and hydraulic conductivity testing records. Of course, this should all be legible, okay, so please check that this information is all provided. Well, I think I actually went ahead of schedule. I'm surprised, but that is pretty much everything I have for today. And you'll find all this information in Chapter 12. All right, all the information that's here. And I want you as a reviewer to check each and every part of the soil testing information and make sure it's accurate, since all of this greatly affects your BMP design. And this obviously falls under your post-construction stormwater management program. And what you're going to see is to throw ahead to module 4. That's where we're going to have design examples that include such checks. So I'm going to ask at this point if there are questions. You can always email me or my coworkers. I can't see the questions, so
Yes, Lisa, I do have something
good
to add about soil testing. The soil testing is a very, very specific and needs a lot of expertise, knowledge. And so as DP, we have to admit that we are not the expert of the soil or the soil testing. We try to research and do the most we can, but we know there are out there, there are still other soil testing method available. So as we stated in the chapter 12, if you can find a recognized source to demonstrate that the soil testing is reliable, and you may use those soil testing. And right now, the most of the recognized testing method we try to use are from an ASTM. So in addition to those like doubling those soil testing method Lisa just mentioned, you may also have the in-lab soil testing method like ASTM D2434, ASTM D5084, and as Lisa mentioned, the STM D3385. Those are all recognized as soil testing, and there are more in STM standards, but you just have to see the conditions and the criteria for each soil testing and applicable situations. Some of the ASTM methods are only applicable to like coarse material, and some more applicable to fine material. And also about the modified cast borehole method that right now in chapter 12 we suspended it, but for the cast borehole method in STM, that still can be used. Just the modified one, we try to modify the case borehole. Still, we still recognize there is a test you can use. So so that's what I want to add. I see one hand raised. Yes, please unmute yourself.
Yes, I wanted to know what kind of soil testing is required as a part of as-built drawing. I just wanted to repeat that section.
Yes, you can see our chapter 12, the post-construction soil testing. There are more details that you can take a look.
Okay, thank you.
Changi, I think Farah Galani has a question. I saw a hand raised for a moment.
Okay.
Yeah, I asked about.
Oh, okay.
soil
Okay.
testing. Thank you.
Sorry.
So okay, so
Oh, we have
Joe
more
has
questions.
yeah.
Yeah.
Hi, Joe.
Is this required for major development only, or for smaller development, smaller design storms?
You mean the soil testing?
Soil testing and requirements for the stormwater management. Is this particular for major development only?
For major development only, yes. What we are talking about here is a major development, but the major development definition in the rules is the disturbance of one or more acres of land, or the increase of a quarter acre of the impervious surface of regulated motor vehicle service. But the township, the municipality, or the pilot commission, they may have different standard to different definition of major development. So you have to check that the applicable ordinance or regulation when you design a development.
Thank you.
Mm-hmm. So if there's no further question, we would like to introduce Dr. McGee. Lisa?
Yes, Dr. McGee, are you able to join us? You probably need a moment to unmute yourself.
Yeah, I believe I've unmuted myself.
Yes, you are good to go. So if you, good afternoon.
Well, good afternoon. It's been very interesting so far. Well, thank you again for inviting me to discuss the NJCAT /DEP MTD verification certification program. And, you know, I've been associated with this program since 2000, first as technical director, and since 2010 as executive director. So it's been a long journey, and it's been a rewarding one. Lisa, can I move my slides, or do you have to do that?
You just tell me when to move along.
Okay, all right, go next slide then.
I'm your Vanna, as it were.
All right, thank you, that's fine. There are about 6 items that I'd like to discuss during this presentation. They're really designed to, first of all, give you a history of the program, describe the current status, give you some idea of future directions, but probably most importantly is give you some cautionary advice. And you'll see that's the next to last bullet. And it's misuse of certifications outside of NJDEP. But it's also, I want you to be careful not to get caught up into the misuse of the certifications also. Next slide. Next slide.
We're on. Can you see it?
No, it hasn't moved.
There was the intro. And we're on the legislature slide. Can you see it?
That's the one I'm looking for.
There may be a glitch in your a lot of people have been having trouble with the internet lately.
Well,
You can't see it yet?
no, I can't see it. The first two came up fine.
Yeah, that's odd.
Okay, there it is.
Got it? Okay.
Okay, a little history. The DEP NJCAT initiative really began back in the late 1990s, and when then discussions between former Commissioner Robert Shin, Governor Jim Florio, and Stevens Institute of Technology President Hal Ravichet identified the need to support the development and promotion of innovative energy and environmental technologies, or what we call IEETS. That resulted in the 208th legislature, which really ran from July 1, 1999 through June 30th, 2020, establishing a technology verification program, Senate Bill number 1750, and appropriate at that point $95,000 to implement the program. I will tell you that is the only appropriation from the state to date to support this program, and it has run on basically vendor money along the way. Next slide. Okay, PL 1999, Chapter 400 is a public law that was passed in January 18, 2000. As we said, support development, promotion of innovative energy and environmental technologies. And the law commonly referred to as the Energy and Environmental Technology Verification Act. It basically outlines the roles and responsibilities of the state of New Jersey, NJDEP, and NJCAT. Next slide. Work then went on from that point in January through basically June, when a performance partnership agreement was adopted between NJDEP and NJCAT. And some of the applicable directives you can read in front of you. It allows for a process to achieve clarification of NJDEP and NJCAT interpretation of laws, rules, regulations relating to review, selection, and verification of technology for the NJCAT verification program. And having said those words, not every technology that comes either to the NJCAT's view or to NJDEP may be a technology that fits for this program. We work with DEP to develop performance evaluation verification processes, and protocols for the purpose of studying these and determining how they might fit into the regulatory program. And both NJCAT and NJDEP, and we do work together to promote the awareness of this program to entities with technology that are likely to be eligible for performance evaluation and verification. Now, to date, NJCAT has focused predominantly on stormwater MTDs, and that's why I'm here with you today. But over the course of those 20 plus years, we verified the performance of certain remediation technologies, heavy metals removal from drinking water, field analytical methods, and combined heat and power systems, to name a few, all those with the support of and in conjunction with DEP. Interestingly enough, right now we're working both with DEP and NJBPU on a new PAP, i.e. Performance Partnership Agreement, to achieve the state's greenhouse gas emissions reduction goals focused on ground source heat pump HVAC systems. This will likely be posted on the NJCAT website shortly, assuming everything goes as planned. Next slide. Seems like we're blocked up again.
All right. Does
Okay.
anyone see
Yeah,
it?
there we are. No problem.
Okay.
I was not on Module 1, but I understand Module 1 went through the history and federal acts predating the post-construction stormwater management program and the MS4 permit requirements. So I'm not going to spend much more time on this. You can read it as well, but states are required to adopt strategies, stormwater management rules to directly address the adverse impacts of stormwater runoff and to meet EPA regulations. Okay, next slide.
Now I'm having trouble advancing things. Hold on. There we go.
Here we go. All right, the major part of my presentation today with that as a background and as a history is to discuss manufactured treatment devices. And as I'm sure many of you know, manufactured treatment devices are called MTDs, are a subset of BMPs, or best management practices. They turn to be proprietary, prefabricated stormwater treatment systems that rely upon a variety of mechanisms to remove pollutants from stormwater runoff. MTDs can utilize settling, particle settling, Stokes' law, for example, you know that, filtration through either organic/inorganic media, vortex separation, adsorptive materials, vegetation, components, and or other appropriate technology. Turns out that that the most interest in NJDEP is removing total suspended solids, which says that most of the activity then is involving settling or filtration technologies. There are other technologies that we have looked at, not for New Jersey, where media have been put in to remove and reduce nutrients, heavy metals, and other things as well. But we're primarily focused on settling, vortex separation, and filtration. Next slide. Okay. You know your stormwater management rules better than I do, but they require major development projects to remove 80% of the project's TSS runoff on an annual basis. As you know, recently, by recently the last few years, this rule has now required the use of green infrastructure, or GIBMPs, that manage stormwater close to its source by, and I know you've had a little on this, and I understand you'll have more information in Module 4, but basically, for a reminder, green infrastructure are treating stormwater runoff through infiltration into the subsoil, through filtration by vegetation or soil, or storing stormwater runoff for use. And we'll talk about that a little bit later in the presentation. As you know, NJAC 7.8 provides approved removal rates for both BMPs and MTDs. And to have a TSS removal rate for manufactured treatment devices, they first must be verified by NJCAT and certified by NJDEP. And I'll be focusing my attention predominantly on that process, on how a technology developer who has a manufactured treatment device wants to get into the game, so to speak, wants to be able to have their product process recognized by DEP to be used to meet the stormwater management rules. Next slide. Okay, NJCAT conducts an independent third-party evaluation to verify the performance claims of IEETs. As you know, many manufacturers will come in and they will claim all sorts of performance-based goals and achievements, but the real question becomes is, what is the basis for those claims? And it's our job to do the verification. The program has strong national and international recognition, excuse me. And I want to say that's predominantly in the stormwater area. We have, we're basically cited in the UK and in France and in Germany. I even seen them in New Zealand and Australia. It's a well-recognized program, and more companies that want to come into the United States by basically leasing their product to a manufacturer here to sell in the States need to get the recognition, the certification from DEP to do that. It's important to realize that MTDs are evaluated against NJDEP protocols. You have set the protocols. Yes, you've done it in conjunction with manufacturers, but these protocols dictate clearly how the performance evaluation must take place. These protocols have evolved from a little after the first one I'm aware was like 2003. There was where the program went through various stages from field verification to laboratory verification, or a combination of the two. The first really solid test protocol was in 2013 for both hydrodynamic sedimentation MTDs and as filtrations. But frankly, we found that the industry learned how to game those protocols and could, by building, for example, interior weirs in their devices and leave a certain amount of sediment in the inlet pipe, they could enhance their performance. So in any event, and by the way, these protocols only allow TSS removal of 50% by an HDS and up to 80% by a filtration device. Key item in here is the last bullet on the page. Stormwater MTDs that have been NJCAT verified and NJDEP certified are the only MTDs that can be used to satisfy the requirements of stormwater management rules for major developments in New Jersey. So where are we? Currently, since the beginning of this certification verification program, there have been 44 MTDs that have been verified and certified by DEP. Now, if you go ahead and you read the numbers underneath there, you'll see hydrodynamic separators, 10, filtration devices, 14, green infrastructure, 9. If you add them up, they're 33, and you said, what happened to the other 11? Well, the other 11 have sunsetted. And what does that mean? Well, they were technologies that were verified, certified under the old protocol back in from 2013. The one that we have determined by implementing it had flaws in it, and therefore they were all given some period of time to recoup their costs. But if they want to continue to have their technology utilized in New Jersey, they have to retest against the new protocol. Eventually, by the end of 2024, 9 of the remaining 10 that were certified under the old program will have sunset dates also. The sunset dates were determined by having a 5-year period to recover your costs in both testing and going through the verification process. But also some people played the game and came in really close to the end. They got approved quality assurance project plans and then went ahead and tested and with the old protocol, finding the flaws in it. So it was felt that we want to have a level playing field by 12/31/2024, and that will happen. And there's one after that because it got caught in between, and that will have a few months beyond that. Why do I spend so much time on this? Because it's got to be very, very careful to you to know which technologies are currently, particularly HDS ones, they're the ones that are affected by this. Which of the HDS MTDs can still be utilized in New Jersey? So they have to be on the list. And if you want to know what the current list is, you have a website that you can go to a link, and you can see the website, which is currently updated by DEP as technologies move in and move out. Shortly, there should be 2 new technologies. I think one may have made it already through the new protocol. One or other one, hopefully that report will be verified in another couple of weeks, and then it'll go into the process. So my advice to you is it's a moving train, and you want to check both the NJCAT website, which will also give you all the data and broken down into those 3 categories, and importantly, the NJDEP website as well. Next slide. I thought I would just spend a few minutes with you giving you some idea of the innovation that has gone into these manufactured devices, and also start getting you conscious of concerns that you have to have, particularly those who do plan reviews. You'll notice here's a device. It's in a vault. You'll see some screens. We'll see a better picture of that in the next slide. Fluid comes in from the left, the inlet pipe.
Sorry.
The screens then basically take out the debris, the trash on the top. The stormwater drops below. You see the sedimentation chambers. Thank you, Lisa. Sedimentation chambers where the particles simply settle out due to gravity separation. Settling, Stokes' law, and then because of the path, of course, over the top, back into the second one, into the third, and eventually out the outside. So this would be what I'll call normal particle separation. Next slide, which gives you an aerial view, top view of it. You'll see the splitter coming in. The fluid is diverted to the left and right. The debris sets on the top of screens. The larger debris, the stormwater goes through those screens, and beneath there, the particles settle out, and then eventually go out at the end. Now, the one thing I want you to realize here is that the inlet and outlet are in line. If you notice coming in on the left and to the right, they're in like a 180-degree pipe in a sense. Why do I tell you that? Because I've seen plans that have been submitted where people want to use these devices with a drop-down grate, or in other cases, they may have 2 inlet pipes. Not this one in particular, but other types of devices, 2 inlet pipes coming in at different angles to what you see the inlet pipe right now. Obviously, such an installation would obviously negate the verification of this technology because it would not operate as it intended to do or as it was verified. Next slide. Many more common hydrodynamic separators are placed in manholes. Here you have again coming in the inlet pipe on the left. There's a flow splitter. We'll see a little bit more about that. There is a oil floatable skimmer in the middle. There's an outlet weir and an outlet pipe. Basically, as the fluid comes in the inlet pipe, it gets split. It can't get by the oil floater skimmers, so it has to go down below that, has to come up the other side, has to go through the outlet weir and through the outlet pipe. Again, a device which is not going to operate properly with a straight inlet pipe and a straight out, unless it's got a straight inlet or a straight outlet pipe. Next slide will show you a little bit about more details. It's clever design. It comes in, it hits this deflector plate, causes 2 rotating vortices behind the plate. That increases through vortex motion, enhanced settling as the particles get removed to the wall. It also increases the retention time. Goes down below the oil splitter, oil floatable splitter. That's that separation and a piece in the middle, and back up and then through holes in the weir on the outside as well as below to the outlet pipe. just two concepts for hydrodynamic separators. Next slide, we'll move to filtration. Very, very common for filtration is to use filters. These are filters that are filled in many cases with perlite or other things as well in a cartridge. These cartridges are placed in a vault. Generally, the fluid again will come into the vault, into an inlet chamber on the upper left-hand side, where larger particles will separate out. Floatables can remain. Eventually, we'll go through an inlet window, which you see into the chamber, and then we'll go through the filters, and then the filters will exhaust down to the bottom, and you'll see they'll go through the bottom of that platform on the outside. These are easily scalable, and in a sense, you could. This one is shown with 2 cartridges. You may see some coming in with 10 cartridges. Obviously, if you're going to scale them, then you need a bigger vault, and there's certain scaling laws that you have to follow. Obviously, inside that vault chamber in there, you're removing sediment by 2 means: filter through the filters and cartridge themselves, but also sediment which is going to fall on the floor of that vault. And it's important that the ratios be kept either constant, or that there's more sedimentation in filtration area, or you're going to affect your filter. You don't have to worry about that, because we check all that stuff, and the certification letter from DEP will clearly indicate what the technologies that have been certified, the dimensions of them, the size, and how many cartridges you can have in there. Next slide. Next slide now is a new concept that's come up. There's been a large indication now into green infrastructures. And in here you see a kind of a curb unit. You see fluid coming in on the left-hand side into a curb. It goes into a kind of a box which has different media. We'll see a little bit more of that on the next slide. And these have the capability of planting as well in between, and they're being used in many places along roadways and whatnot in downtown areas. The filtered material then goes through the media and at the bottom, you see filtered at the bottom. Next slide. This gives you, for this particular thing, you see here, there's a shredded mulch on the top. There is an engineered media, which is engineered predominantly to remove the sediment. And then you typically have a gravel media on the bottom and a perforated pipe. Now, these devices can be, but I've not seen them yet, can be used to infiltrate directly into the ground. New Jersey requires, to meet the green infrastructure designation, that you be able to infiltrate 100% of the treated stormwater into ground. In other words, nothing can go out the perforated pipe. So even if you could do 10% infiltration and 90% through the perforated pipe, say to a stream or a treatment or something like that, it would not qualify as a GI, green infrastructure, by the ruling in the department. And I'm sure you'll learn more about that in Module 4. All right, next slide. Okay, critical slide, because you need to be up to date that you not misuse your certifications. So the first point I want to make is that not all NJCAT verified stormwater technologies are NJDEP certified. And you say, well, why would you verify it? Well, there are certain manufacturers that want to follow the protocol with one exception. And the biggest exception is they want to use a different sediment particle size distribution, or what we call a larger D50. 50% of the particles are smaller than, and 50% by mass are larger than. The NJDEP PSD requirement is 75 microns for D50. which, you know, involves clay sill that's very representative of what you might get in New Jersey. There are certain other states that, because they don't want to have filters, they say, well, can you do something called, and it was used to be called OK 110, excuse me, which had a part size of 110 microns. So some have gone in and they verified their performance, which obviously means they can get 80% removal with a smaller unit because they're dealing with a larger particle size. They're not going to help you in New Jersey. And it's interesting how many other states I'm hearing don't understand the difference between NJCAD verified and NJCAD verified and NJDEP certified. And it says, again, this occurs primarily with HDS separators, allows for smaller units. Only 20% of the currently certified stormwater technologies are GI certified, and this number has grown steadily since 2020. I have another one which I just submitted, just got through the process, and it was just submitted this week to DEP. So this is going to be your big growth area. Okay, only the and this is the other important point, only the HDS MTD configuration that was tested has been NJDEP certified. If you recall earlier, I pointed out the inlet and outlet pipes being aligned. Their manufacturers will frequently offer other configurations claiming certification. These include inlet outlet configuration that is not 180 degrees apart. For example, it might come in at 90 degrees to the outlet. Multiple inlet pipes. I've seen some plans being submitted, got people calling to my attention, where there are 2 inlets into a device and this was not tested, or as I mentioned previously, people might use grade inlets. Now, in the new protocol that's out, manufacturers can test inlet outlet configurations that are not 180 degrees apart and get certified for it. It's spelled out in the protocol, but to date, nobody has done that. So be aware that that it's only the configuration that was verified and certified that can be used in New Jersey. Next slide. Another potential misuse of certifications is what is called online or offline installations. One of the concerns with an MTD is if it's online, that if you get a higher flow rate through than what you've installed it for, what we call the manufacturer treatment flow rate, say it's 1 CFS, and all of a sudden you get 2 CFS going through the unit, what will happen with the sediment that has been collected? Will you scour it out? So the protocol requires, if you want to be online, that you have to basically go ahead and test for scour up to 200% of the MTFR, manufacturer treatment flow rate. If you're going to be offline, then you have to test at 125, and that allows for a slight variation, but then that requires a bypass on the upstream system, obviously, so that the MTD does not see that higher flow rate. But this is clearly spelled out in the certification. It's on the NJDEP website, and you can refer to that and make sure that that the unit has been being properly installed per the certification letter. Next slide. Okay, what about the program moving forward? We've been looking back. We're looking at its current here. First of all, we've on the technology verification database, that's NJCATS, we've expanded and added explanatory text. It was hard for a lot of other people to understand the various categories. So we now have 4 categories: stormwater technology, which are laboratory verified and NJDEP certified, so people can look at them real quickly. And they're broken down into the 3 major areas: green infrastructure, hydrodynamic separators, and filtration MTDs. We then have a category, stormwater technology, which are laboratory verified. And I told you that's when someone wants to basically use an existing protocol, but slightly modify it. The most common is the larger particle size, D50. Stormwater technology public review. The process to get verified is really extensive. Once I agree with the manufacturer on a verification report, after evaluating all the test data by an independent laboratory and whatnot, that report then gets sent out for public review. The public review is probably about 40 people on my distribution list. It keeps growing. Generally, it's basically all those who are involved in the industry, particularly other manufacturers, and they scrub that report like crazy because they're in high competition. So you'll see sometimes reports that are in public review, and I cannot move them out and declare them to be verified until I've satisfied all the review comments. And then there's that other category of other energy and environmental technologies. There are not many which have been verified in the past, but there's all explanatory text to help that out. Now the question became with the manufacturers, well, what are you going to do with verification reports that were verified, in some cases certified against prior testing protocols, even though we have found shortcomings in those protocols? So we now have 3 other archive categories: stormwater technologies that were verified, previously certified, stormwater technology laboratory verified against HTS, and field verifies, which were very, very early in the NJDEP program back in the early 2000s. We did some field verification, but frankly, they were bare. Mother Nature is not your friend, and it's hard to get anything. So in any event, if you go to our webpage and you check verified technologies, verification database, all this is laid out with the appropriate text so you know what's what. But from a regulatory viewpoint, the only category that you can use in New Jersey are that first category above, laboratory verified, NJDEP certified. Next slide. I think it's the last one. Okay, as we're moving forward, we're in the process of implementing new HTS protocol. I believe there's only been one technology that's gone through it. We'll no longer be crediting sediment deposit in the inlet pipe. We've already managed the sunset of 11 technologies that can no longer be used. We talked about some that are currently still certified and that will be not. ASTM, American Society of Testing Material, has now established a committee, E64, which is developing ASTM standards based on the NJDEP laboratory test protocols. We've really taken the lead in the nation here in establishing testing protocols to get performance. There are 8 MTDs that were verified only. They will sunset in the next 2 years, also 4 this year, 4 next year. And finally, there's a new initiative called the Stormwater Testing and Evaluations for Products and Practices Initiative. It's heavily manufacturer driven. I'm personally a little nervous about it because only those who pay dues get to vote, and they are trying to impact the whole process. I think it will not get processed. It won't affect New Jersey. But everybody's trying to get an edge and getting away from a fairly rigorous program, which we've put in place. New Jersey should be proud of, NJCAT is proud of. And again, I want to say it's a partnership between the 2 organizations. I believe that's it. Lisa, next slide gets us to questions. And I know it was quick, but I know people can't wait to get to the quiz. So let's see what, if anything, people would like the questions.
All right, while we wait for the quizzes, one thing I will mention, Dr. McGee mentioned the archive. So many projects take years from when they achieve or receive local approval, and then by the time they actually get built, they realize, oh, wait, those filter cartridges are going to add an additional expense. So perhaps we should pick something else out. So that you'll have to go to the archive, look at the information that was in that device. And if you need help figuring out what is a suitable replacement, please reach out to us.
Excellent point.
Do we have any questions, Changi? Or Manesh?
I don't think they fell asleep, but I don't know.
Okay.
Well, again, I
Let me
thank
just
you.
see. Let me see if I
thank
can
you for-
find the other chat. And if not, then I'll advance the slide. And I am not seeing any further questions that haven't been answered. So thank you very much, Dr. McGee.
Well, thank you
as
for inviting me, and good luck on the rest of the next 2 modules. And good luck on the
Okay.
quiz, guys. All right.
So Peter is next, and he's going to administer quiz 2, and including the review. And of course, in a moment or two, we'll provide you with the QR code in the chat, the link, all of that, so that you can hopefully have a better quiz experience than yesterday. So please stand by while I hand over control to Peter. And I'm not sure if the quiz is turned on yet, so don't panic. We will take care of it. Thank you, everyone.
All right, yes. So I will share my screen now. Hello, everybody. I would like to confirm that you guys can see the slide.
I can see it.
Yes.
All right, thank you. All right, so let's get right into it. And I will say now the quiz has been opened. So just to let you all know that. And so let's get right into it. So we're going to take quiz 2. As noted before, it is important to complete the quiz now during the time allotted. Note that you cannot move forward to complete a quiz or complete a quiz at a later time. And we need the quizzes to be completed in order to issue credit for the class. So let's get to the quiz. So just like Tuesday, there are a few ways you can get to the quiz, as the others have mentioned. The link in the middle of this slide will take you to a page on our website, which includes the handouts as well as each of the quiz links. You can click the link for quiz 2 found at the bottom of that page to be taken to the quiz in SurveyMonkey. Another way is using the link at the bottom of the slide, which you're also going to find posted in the chat, that will take you right to the quiz in SurveyMonkey. Make sure to do this in a separate tab in your web browser if you follow that method. And then lastly, if you want to take the quiz on your phone, you can scan the QR code on this slide, which is also in the chat, and you'll be taken right to the quiz. All right, so a few other quick notes here. You must answer every question before you can advance to the next screen and finally submit. You may only take the quiz once. And we're going to allow 20 minutes to take the quiz. So it's 3:26 right now. So let's say 3:47, you have until then to take the quiz. And if you do finish early, you can take a short break until that time comes. After this time, we will review the answers to each question from the quiz. The review portion of the quiz is part of the course and for credit and attendance, so please do not leave after completing the quiz. We're not going to keep it for too long. Here's everything all in one place. You may now begin the quiz.
Hi, Mr. Welter. Yes, we're still live. Thank you, everyone who's completed the quiz already. And for those of you still taking it, please keep going. We have about 5 more minutes, but my analytical software is telling me that about 80% have completed it. So we need to give everyone adequate time since it counts for so much. All right, 5 minutes. So if you're done, stretch your legs, get a beverage, and please be back by 3:46 or 3:47. Thank you.
All right, everybody, it is now 3:47, so we're going to get right into the.
Peter, your
Sorry
audio
about
cut
that.
out.
We're going to get right into the review here, and let's get to it. Okay, so the first 3 questions on the quiz were general information types of questions. So we will begin here at question number 4. True or false? There is no longer a minimum or default value that can be used for time of concentration using the NRCS methodology. meaning this value must always be calculated. And this is true. There is no longer a minimum or default value that may be used for the time of concentration. Time of concentration, or T sub C, for pre and post construction conditions must be calculated based on the flow path. As you recall, Anthony went over this in the first presentation from today in the calculations. Number 5. According to the NJ Stormwater BMP manual, what is the maximum roughness coefficient that can be used for sheet flow calculations? Correct answer is A, 0.4. The value of 0.4 is the only roughness coefficient that can be used for wooded conditions. Number 6. What is the maximum sheet flow length for the pre-construction condition, assuming there is no physical constraint present to prevent sheet flow from occurring? 100 feet is the correct answer. For the pre-construction condition, the maximum distance for which we can assume sheet flow occurs is 100 feet, unless there is something physically in contact with the flow of stormwater runoff, such as a swale, curb, or inlet, to prevent sheet flow from occurring. Remember to use the actual distance if it's less than 100 feet. So this comes from Chapter 5 of the BMP manual if you haven't taken a look at that yet. And just remember, again, to use the actual distance if it'll be less than 100 feet. Number 7. According to the NJ Stormwater BMP manual, what is the maximum drainage area to which the rational method can be applied? And the correct answer is 20 acres. If the coverage of the site is greater than 20 acres, do not use the rational method in that scenario. Number 8, true or false? When using the NRCS methodology for directly connected impervious cover, averaging pervious and impervious curve numbers is permitted for calculating a hydrograph. This statement is false. So here's a quote from NJAC 7:8, 5.7A4. In computing stormwater runoff from all design storms, the design engineer shall consider the relative stormwater runoff rates and/or volumes of pervious and impervious surfaces separately to accurately compute the rates and volume of stormwater runoff from the site. Keep in mind, this statement does not apply when using the NRCS composite CN with unconnected impervious area method. See Chapter 5 of the BMP manual for more information. Number 9. When determining the curve numbers for site design, the design engineer should assume that the conditions of the existing cover is good condition. That's the answer. This is fairly straightforward. Pre-construction condition curve numbers should assume that vegetated areas are in good condition. Number 10. Yes or no? Can the Delmarva Dimensionless Unit Hydrograph, or DUH, be used for the redevelopment of a 2-acre, entirely impervious site located within the coastal plain? And the answer to this is no. The Delmarva Dimensionless Unit Hydrograph must be used when modeling watersheds within the coastal plain region of New Jersey, with just a few exceptions. It cannot be used to size a manufactured treatment device, or MTD, as it may underestimate the peak flow rate entering the MTD. Also, for an entirely paved site, the significant surface storage associated with the coastal plain is no longer present, also resulting in underestimated peak flow rates if the Delmarva is used. And then additionally, the Delmarva should only be used in areas that have an average watershed slope less than 5%. If any of these situations are proven to be present, the SES Standard Dimensionless Unit Hydrograph must be used. Also, a side note on this subject, if the Delmarva is used in the pre-construction condition, it must also be used in the post-construction condition. Same idea goes for the SES. Number 11, True or false? If the NRCS methodology for calculation of stormwater runoff is used, the Type 3 rainfall distribution must be used for developments in New Jersey. And this is false. As heard from Anthony today, NOAA C or D distributions must be used, not the Type 3. Number 12, true or false? Pretreatment must be incorporated into the design of a small-scale GIBMP that has a drainage area greater than 1 acre, infiltrates runoff into the subsoil, and uses exfiltration in the routing calculations. This statement is true. All small-scale GIBMPs, which are designed to infiltrate into the subsoil and have contributory drainage areas greater than 1 acre, must include pretreatment of stormwater runoff when using exfiltration in the routing calculations. Question 13. Soil testing logs prepared in accordance with Chapter 12 are required for which of the following BMPs? The answer to this is all of the above. They all have a minimum separation from the seasonal high water table, which you can find in their respective BMP manual chapter. Soil testing would therefore be required for all of these to ensure that they meet the required separation. Number 14, true or false? A factor of safety of 2 must be applied to the slowest tested saturated soil hydraulic conductivity rate to determine the design saturated soil hydraulic conductivity rate, which is used for infiltration BMP calculations. And that is true. Since the actual saturated soil hydraulic conductivity rate may vary from soil testing results and may decrease over time, a factor of safety of 2 must be applied to the slowest tested saturated soil hydraulic conductivity rate to determine the design saturated soil hydraulic conductivity rate. Computing a BMP's drain time for the maximum design volume, the exfiltration rate for a BMP allowing exfiltration in the routing calculation, or the infiltration rate in the groundwater mounting analysis must all use the design saturated soil hydraulic conductivity rate. Number 15, yes or no? During the month of July, can the seasonal high water table be determined by measuring water levels directly within soil profile pits or borings? The answer to that is no. So you can determine the seasonal high water table by measuring water levels directly within soil explorations between January and April only. Other options to locate the seasonal high water table include observing modeling showing redoxomorphic features, which can occur at any season of the year, and then also using the NRCS Web Soil Survey during the months of May to December. All 3 options have their own steps and exceptions though, so please see subsection 1D of Chapter 12 of the BMP manual for full details on each option. Number 16. When is it necessary for the design engineer to assess the hydraulic impact on the groundwater table? And the answer to that is whenever an infiltration BMP is proposed. You should assess the hydraulic impact on the groundwater table anytime an infiltration BMP is proposed. This would include any potential drainage issues and potential damage to nearby structures. Number 17. How many soil profile pits and/or soil borings must be performed for 5 small-scale bioretention basins and 1 mapping unit that are each 450 square feet and scattered around a development? Correct answer is C. So we know from Lisa's soil testing presentation that if an infiltration BMP has an infiltration area that is less than or equal to 500 square feet, you would have to do a minimum of 1 soil profile pit per soil mapping unit. You would also have to do 1 soil boring per BMP as well. If the BMPs are going to be located in different soil mapping units, Each unit must have one soil profile pit. But if you read the question here, the 5 basins are going to be in one mapping unit. So in total, one soil profile pit for the one mapping unit in this example, and then one soil boring per small scale bioretention basin. Number 18, true or false? In a small scale infiltration basin, the 2-foot separation from the seasonal high water table should be measured from the surface of the sand layer. And that's false. As stated in the BMP manual, for any designed infiltrating BMP, the separation from the seasonal high water table needs to be measured from the bottom of the sand layer, which is the lowest excavated elevation in the BMP. We mentioned the seasonal high water table separation requirement when we talked about why the soil testing is important. Number 19, where on the soil horizon should soil permeability tests be performed when no soil replacement is proposed? The answer to that is A. Soil permeability tests must be performed on the most hydraulically restrictive soil layer below the BMP and above the seasonal high water table or bedrock, to the greater of 8 feet below the lowest point of the basin or 2 times the maximum potential water depth, as the permeability of this layer will be the limiting factor in infiltration rates. Number 20, true or false? When choosing a hydrodynamic separator type MTD, the inlet configuration, such as the angle and number of inflow pipes, must strictly match the inlet configuration described in the NJCAT verification report. This is true. So manufacturers will try and offer other types of configurations, but this is not allowed. They must not deviate from the tested and certified configuration that the MTD was meant to be in, as they would not meet the certified TSS removal rate. All right, everybody, so that's the end of the quiz review, and that's also the end of Module 2.